showed it 5 minutes, just like Rich did, and then we tried to end it in 5 minutes, and there's some time for questions. So very good. So we have a nice session here. We're starting with Mihailo Jovanovic, talking about oblique transition in high-speed separated boundary layer flows. I guess everybody who does transition in the States is doing hypersonics now.
Everybody and their grandma.
So
yes.
we will maybe understand why, or maybe not, after you talk. Thanks.
Thank you, Dan. Thanks for clearly specifying the rules of engagement. It's an absolute pleasure to be here, and it's I'm thrilled actually to see all friends and familiar faces in the audience. So as Dan mentioned, I'll be talking about oblique transition in high-speed separated boundary layer flows, and this is a joint work with my postdoc Anubhav at USC and our collaborator Siddharth from Los Alamos National Lab. And separated boundary layers are ubiquitous in high-speed flows over complex geometries, and they involve shock boundary layer interactions, and they're characterized by the appearance of different shocks, in particular both separation and reattachment shocks, and the presence of small recirculation zone. And a canonical flow configuration that is shown here is given by double-wedge geometry, where you have two plates at different inclination angles that meet at a corner around which this separation bubble forms. And this geometry has been recently used to probe transition in hypersonic flows and to gain insight into the underlying mechanisms and what is going on. And very careful experiments have been conducted using oil flow visualization and temperature sensitive paint by Texas A&M and German/Russian groups. And what these experiments showed, they demonstrated appearance of these steady streamwise elongated structure that have particular preferential spanwise length scale and these structures exist both in recirculation zone and after the reattachment, and reattachment line is shown here. And these structures, they are typically associated with persistent local peaks of heat flux and wall temperature, and they are widely believed to serve as a precursor to transition to turbulence further downstream. And for hypersonic vehicles, transition is a huge issue because it imposes heavy thermal loads on vehicles that can compromise even vehicle safety. And these studies, they motivate our work. The objective of our work to examine the origin of reattachment streaks in separated flows and to understand the triggering mechanisms behind transition to turbulence in these flows. And the setup that we are going to consider is given by an adiabatic double wedge with realistic conditions that were used in this experimental study. So numbers are given here. Free stream Mach number is 5 and free stream Reynolds number is roughly 200,000. And the very first thing that you should do pretty much in any flow configuration is to determine the base flow, the laminar flow, the steady state solution of, in this case, compressible Navier-Stokes equations. Unfortunately, there is no explicit solution, no explicit characterization. You can't go to MATLAB and compute this solution. What we did, we utilized finite volume scheme that was developed by Graham Candler at the University of Minnesota to compute this 2D base flow. And this 2D base flow is a function of streamwise and normal coordinates in the typical traditional Cartesian coordinate system. Once you have 2D base flow, you can ask a number of questions. For example, you can study linear stability properties, and this study was done a few years ago, and Graham Candler and his group at the University of Minnesota, they showed actually that for these experimental conditions, there are no modal instabilities around the underlying 2D base flow. Namely, entire spectrum is in the stable region, which implies that your 2D base flow is globally stable to three-dimensional perturbations. So if you were hoping that eigenvalue analysis is going to give you insight in terms of transition mechanisms, unfortunately, spectrum is in the stable region, and this analysis turns out not to be very informative. And because of that, what we would like to do, we would like to probe compressible Navier-Stokes equations from slightly broader point of view. Namely, we would like to examine fluctuation dynamics around 2D base flow that I call psi naught in the presence of an additive source of excitation that can, for example, account for imperfections in the free stream. And I would like to ask a question of how does the compressible Navier-Stokes dynamics maps this source of excitations into quantities that we care about, flow fluctuations, right? And again, here D is the external source of momentum, mass, and total energy, both kinetic and thermal energy. Psi is a vector of velocity, density, and temperature fluctuations. F is generator of the compressible Navier-Stokes dynamics, and 2D base flow psi naught is a steady state solution of compressible Navier-Stokes equations, right? It solves this equation where F is again dynamical generator of compressible Navier-Stokes equations. In order to make some progress, we are going to confine our attention to small amplitude forcing. Namely, I'm going to assume that my forcing is of small amplitude. And if I invoke this restriction, this allows me to tap into weakly nonlinear framework and to represent velocity flow fluctuations in terms of the power series expansion in, where small parameter is amplitude of the forcing, right? These different coefficients in this expansion capture velocity fluctuations up to a certain, flow fluctuations up to a certain order. T here denotes time and X is a vector of spatial coordinates. And weakly nonlinear formulation allows us to obtain conveniently coupled system of equations that are easy to analyze, and in contrast to some of earlier talks today, actually quite informative. Hopefully by the end of my talk, I'll be able to convince you that weakly nonlinear analysis captures the essence of the story of what is happening in terms of transition in this high-speed compressible separated flow, right? So if you do weakly nonlinear analysis, dynamics at order of epsilon is given by linearized flow equations that are driven by external source of excitation, and A here denotes linearized dynamical generator of compressible Navier-Stokes equations that is parameterized by the underlying base flow, right? So these are standard linearized equations that were used in stability study with one additional ingredient that I would like to use as a driver in order to figure out how corresponding flow fluctuations are going to behave in the presence of this driver. At order of epsilon squared, you again obtain linear system of equations with the very same dynamical generator as for linearized equations. But now the driver is given by nonlinear modulation of the output of the linearized equations, right? You compute flow fluctuations for the linearized equations, you nonlinearly modulate them, and they enter now as a driver into this order of epsilon squared term, right? And so on. You can do this up to an arbitrary order, and the common theme is that for all of these equations, the very same linearized dynamical generator appears in the mix. So the very first thing that you need to do is to understand properties of this linearized dynamical generator. And what we would like to do, we would like to restrict our attention to deterministic forcing that is purely harmonic in the spanwise direction, in z direction, and in time, and deterministic in streamwise direction and in normal direction. And Fourier decomposition in time and in spanwise direction is not restrictive because of time invariance of the underlying base flow and translational invariance in the spanwise direction, right? And if you substitute this into linearized Navier-Stokes equations, because of stability, the steady state response of the linearized equations is going to be also purely harmonic with identical spatiotemporal frequency pair, but with a different amplitude and phase. And amplitude and phase are going to be contained in this function psi1 hat, which is now a function of streamwise coordinate and of wall normal coordinate. And the object that is important in this study is the spatiotemporal frequency response operator. Namely, this is the operator that maps for any given pair of kz and omega. It maps an input function of streamwise and normal coordinate into the output function of the streamwise and normal coordinate. And this operator contains identical information that you have in linearized compressible Navier-Stokes equations, right? So you would like to gain some insight into this operator. In the simplest possible context, this operator is nothing but a resolvent operator, and singular value decomposition can be used to characterize amplification as a function of span-wise wave number and temporal frequency, and to identify, to decompose essentially input and output modes, inputs and outputs into orthonormal modes whose importance can be characterized by the corresponding singular values. And this is what resolvent analysis does for you, right? Resolvent analysis essentially brings insight into the properties of the spatiotemporal frequency operator or resolvent operator in the simplest possible case by doing singular value decomposition, right? And the largest amplification across any pair of spatial and temporal frequencies is given by the maximal singular value of the resolvent operator, of the frequency response operator. And physically, it's an important quantity because it gives you the worst case ratio of the energy of the output that you care about to the energy of the input, right? In the talk that was couple of 3 talks above, energy of the output and energy of the input were measured differently. You were paying attention to streamwise velocity fluctuations, and the input there was initial condition involved normal and span-wise. Here, I'm going to assume that I'm forcing in all possible directions, that my forcing is entering into every single component of compressible Navier-Stokes equations, and fluctuations energy is going to be quantified by so-called choose energy norm, which not only accounts for kinetic energy, but also for energy of density and temperature fluctuations. And an excellent reference on this topic is given by Hanifi and Henningsen in this physics of fluids paper, okay? So what I'm going to do now, I'm going to take a look at how this worst case amplification depends on the temporal frequency and on span-wise length scale, essentially 2 pi divided by kz. And this is pretty informative plot. This is a plot that shows the worst case amplification, the maximal singular value of the frequency response operator as a function of temporal frequency and as a function of lambda z, which is 2 pi divided by kz. And what you notice here is the presence of these 2 strongly amplified regions that are located in the region of small temporal frequencies for roughly order of 1 value of lambda z. And there is another region here, which is taking place at order of 1 values of temporal frequency and lambda z as well. So this region here is associated with streamwise streaks, which are roughly steady, and this region here is associated with oblique modes, right? And the length scale of oblique modes here is roughly twice the length scale of the underlying streaks. It's also instructive to take a look at the dominant input-output pairs. If you take a look at the spatial structure of the inputs that are causing this largest amplification for this point and this point, they take the form of streamwise vorticity inputs, which are localized upstream of the corner. This is the most effective way to trigger your double-wedge flow, and the corresponding response is actually downstream of the corner. I would like to highlight that we haven't made any a priori restrictions here on where input should enter and where we are paying attention to outputs. This is what resolvent analysis tells you. If you want to trigger this flow at the level of linearized dynamics most effectively, you should force in the region which is upstream of the corner, and your flow is going to respond downstream of the corner, okay? This is what we concluded so far. And again, summary of what I just told you is listed here. We identified 2 strongly amplified regions, the one that corresponds to steady streamwise streaks, which are triggered by upstream vortical inputs, and another one that is corresponding to unsteady oblique waves. And I'd like to highlight that we studied in detail the importance of steady streamwise streaks in slightly different geometry a few years ago in the JFM paper. What I want to do today, I want to pay attention to this second region here. I want to see actually how nonlinearities impact oblique waves and what happens with them. And the reason why we want to do this is because in most wind tunnels, you experience unsteady free stream disturbances. And the question that we want to answer is whether unsteady disturbances can trigger steady streaks. Okay. Again, the rest of my talk is going to be paying attention to flow structures that correspond to this peak. And the question that I want to ask is, even though these unsteady flow structures, can these structures trigger steady streaks that were observed in these experiments that I used as a motivation for my study? So if Navier-Stokes equations were linear, the answer to this question would be no, of course. Why? Because if you introduce oblique wave forcing with particular span-wise wave number and pair of temporal frequencies, which are different than zero, then laminar base flow would be modulated by oblique waves with the same spatio-temporal frequency pair, right? You wouldn't be having steady component in your response, right? But Navier-Stokes equations are not linear, and weakly nonlinear analysis tells you that in addition to this order of epsilon modulation that takes the form of oblique waves, you also have this order of epsilon square modulation that contains purely harmonic components, but it also contains a steady modulation to your laminar base flow, which takes the form of steady streaks. Steady because there is zero temporal frequency associated with this, and the span-wise wave number of oblique waves was doubled, right? Whoever has done weakly nonlinear analysis shouldn't be surprised by this, but this is what comes out of it, right? And big picture summary of what weakly nonlinear analysis does for you, if you introduce unsteady upstream forcing into your problem around laminar 2D base flow, at order of epsilon, you're going to obtain oblique waves, and at order of epsilon square, nonlinear quadratic interactions of oblique waves are going to trigger steady streaks, and objects that are essential in the process of generating these are resolvent operators evaluated at these different pairs of span-wise wave numbers and temporal frequencies. If you want to understand weakly nonlinear analysis, you need to pay attention to these two resolvent operators. And this is what we've done essentially. And just to give you a graphical illustration of how this process works, if I trigger my flow by an upstream oblique wave disturbance, at order of epsilon, I'm going to have oblique waves. At order of epsilon squared, I'm going to have steady streaks. And what I'd like to highlight is that oblique waves, that they appear in this region, which is slightly further away from the place where separation bubble takes place. And as a consequence, the corresponding forcing that they trigger into order of epsilon squared dynamics induces streaks that are spatially localized in the region which is essentially moved near to the reattachment point. Okay, and in spite of this difference here that I'm going to highlight in a moment, what I'd like to highlight is that unsteady interactions generate steady vortical forcing, which is localized downstream in contrast to the steady primary forcing that came out of the analysis of linearized Navier-Stokes equations and the streaks that are triggered by linearized Navier-Stokes equations. And primary contribution of the forcing comes actually through vortical component. And what I'm showing here is the much larger amplitude of these vortical excitations that come out of resolvent analysis at the secondary level relative to other forcing components. Okay, so obviously the question at this point is, you know, why should we care about anything that I told you so far, and why this should have relevance in such a complex separated high-speed flow? And the only way for me to test utility of things that I presented so far is to go to DNS and to see what DNS tells me and to compare our theoretical predictions to what DNS gives us. And in order to do that, we have actually conducted DNS with varying forcing amplitudes. In fact, this plot here shows energy of steady streamwise velocity fluctuation for 4 different amplitudes. So I'm changing here base amplitude by 3 orders of magnitude, okay? And if you scale these plots, I'll be done. I promise to be well behaved, so I'll keep my promise. So if you scale these plots with amplitude squared, A naught here is epsilon, essentially in my weakly nonlinear expansion, what you observe is that all plots collapse on each other. All DNS results collapse to each other, at least in the separation bubble, and you have complete agreement with the results of predictions of weakly nonlinear analysis in separation bubble. There is disagreement only for the largest values of forcing amplitude that we used, and this disagreement is moved outside of the separation bubble. So in this problem, weakly nonlinear analysis captures the essence of the story and confirms, actually our results were confirmed in direct numerical simulations of compressible Navier-Stokes equations. Another thing that is very insightful and interesting is representation, and also important in the context of lower order decomposition, is representation of the steady streak response in terms of resolvent modes. Modes of the resolvent at 2 times kz, where kz is spanwise wave number of oblique modes and omega equal to 0. If you do that, you can represent streaks as a linear combination of output resolvent modes, where corresponding coefficients are given by a product of the corresponding singular value and this projection term that projects forcing to order of epsilon squared dynamics to input resolvent modes. And here are singular values of the resolvent operator at omega equal to 0 and 2 times kz. There is dramatic difference between the principal singular value and the second one. On the other hand, if you evaluate these coefficients a n, it turns out actually that the biggest contribution to the response is given by the second resolvent mode, second output resolvent mode. Even though there is 1 order of magnitude difference, projection of this nonlinear modulation of psi1 on the second suboptimal output mode is much bigger, right? So this tells you perhaps that if you were just to use rank 1 approximation of your operator, that perhaps this wouldn't be the most prudent thing to do. And even more interestingly, if you compare spatial structure of steady streaks to second output mode, you obtain striking similarity between reattachment streaks and the second output mode throughout the computational domain. Okay, so second output mode, second singular value plays an important role in this problem. We still don't know why, and we are trying to understand why this is exactly happening. We have confirmed our results in DNS as well. We have conducted very careful DNS study, and what we showed actually is that oblique waves represent potent mechanism for triggering transition to turbulence, and transition to turbulence happens actually very close to the reattachment line. So this brings me, I have 2 more minutes according to my watch, brings me to the last slide of my presentation. So let me just briefly summarize what I told you. So essentially we studied the origin of streaks, steady streaks in high-speed separated flows, and we demonstrated that streaks represent robust responses to both steady and unsteady disturbances. Steady disturbances at the primary level, at the level of linearized dynamics, and unsteady disturbances at the level of weakly nonlinear analysis at order of epsilon squared. It turns out that steady vortical excitations can be generated by quadratic interactions of unsteady oblique waves. And as our DNS demonstrated, this provides an effective route for triggering transition. I didn't get a chance to talk about this, but we understand physical mechanism very well. And physical mechanism is contained in our archive post that is currently under revision for JFM. Physical mechanism is very different relative to what you're seeing in attached boundary layers. That separated flow features play a dominant role in the formation of both oblique waves and streaks. For oblique waves, curvature of the separated shear layer in recirculation zone, I can't pronounce that word, recirculation zone, right? Plays, I'm not going to pronounce it from now on, curvature of separated shear layer plays a dominant role. And for streamline deceleration near reattachment is the dominant physical mechanism. That's pretty much all I wanted to tell you. I'd like to thank sources of funding, Anubhav and Siddharth, for their great and hard work. And if you want to reach out to me, this is my contact info. I would prefer if you talk to me in person. Thank you.
Thank you very much. Thank you for keeping the time very well. Any questions? Now we have 5 minutes.
Tim.
Thanks, Mihailo. Oh, okay, great. Yeah, so I was just wondering about the shocks. So all your domains seem very zoomed in. Are you including the shocks?
Everything is included. Everything. Shocks are included completely. They are captured. They're an integral part of, yes, they are.
Aren't you worried about linearizing the shock dynamics, especially when you go to the weakly nonlinear regime?
Am I worried or not? Right. If I put my hat of a mathematician, yes, I am. Right. But at the same time, people are doing this all the time. Are there issues with these type of things? I don't know rigorous answer to your question.
Well, Joe, one of your co-authors, in fact, Joe just published a paper where they were doing a kind of elaborate procedure to go back and forth between US3D and the linear analysis to try to get that right. But
I see.
I mean, you're very zoomed in the separation region, and maybe it doesn't matter for your results.
See, I to be honest with you, we haven't done this. We haven't done this. I haven't talked to Joe in ages, so I should probably call him to see whether whatever I presented here is inconsequential, right? But I see your point. I see your point, right? I mean, it's this certainly should be verified. If there are some issues, I should become aware of them. But from what I've seen, everything that we do at the level of input-output analysis is pretty robust. And this has been my experience even in canonical configurations. If you take a look at, let's say, robustness of eigenvalue decomposition, there are lots of issues with that. Once you start dealing with actually input-output framework where you compose resolvent with adjoint and so on, things on a much firmer ground. You're bringing another set of issues, though, whether discontinuities in the base flow are causing any potential issues there. And I don't know answer to that question right now, but we should certainly pay attention to that.
All right, thank you.
Okay. Anybody else? Yeah.
Mihailo, very nice talk.
Thank you.
My question is, did I understand you correctly that for compressible Navier-Stokes, there are no Gertler modes? The Gertler instability modes don't exist, or I misunderstood?
See, they are not present in terms of model instabilities, but curvature plays an important role in triggering oblique modes, right? So if you just want to pay attention to Gertler instabilities, they are not there for these particular conditions that we looked at. Having said that, curvature of the shear layer is essential for triggering oblique waves that ultimately led to transition to turbulence, right? So curvature is still important even in the absence of model instabilities.
There is another problem, and just I'll say that briefly, and we can talk later, and that's the stagnation flow in front of cylinder. And the early work had to do with heat transfer, but there's some literature that could also relate to what you've done, but not as elegant or as complete as what you present.
Sure. Thanks. I'll be happy to chat more.
We have time for one. It's over here. One quick question, and I think we can start changing.
Is in the line of the same previous question. So the weak mode, it is uncentrifugal instability, perhaps. And the important point is to know the order of magnitude of the wavelength. My question is, the wavelength of the oblique modes is the order of magnitude about half of the thickness of the separator?
That's a good point. That's a good point. Let me tell you exactly what it is. So this lambda z in this plot here, all lengths are scaled by thickness of boundary layer at the separation point. Okay, that's the relevant.
Because the question is, perhaps the Strix scale with the boundary layer in the outer part of the outside, and the oblique centrifugal instability need to scale with the part of the basic flow is unquet Poisson flow because there is circulation. So this is perhaps the question to the physical understanding of the origin of the.
What we are showing here is that the length scale of these is the span by is half of this. It's roughly what primary amplification already identifies. But you're probably talking about something else, so we should probably continue this conversation offline. Thank you,
great.
guys.
So thanks a lot, and we say thank you to Mihailo again. Thanks. So now we have the